Great. Well, firstly, thank you for inviting me here today to talk about our work in augmented reality displays. DigiLense comes from a backdrop of military and aerospace. We developed some early prototypes and have been heavily involved in night vision and advanced avionics platforms for heads-up displays. And latterly, we produced the first waveguide display for civilian aircraft, which is now FAA approved and in service. And what I wanted to do today is explain a little bit about waveguide optics and waveguide displays and show you some of our latest work as we move into consumer applications from the heritage in these military and commercial applications in that regard. So the key to our technology, and indeed we think the breakthrough in waveguide optics, is the material systems. And this took us nearly 8 years to develop. It's a fundamental new class of nanocomposite material system, which when phase separated, which I'll explain a little bit in a moment, allows for these nanoscale holographic structures to be written into a waveguide. And with that, we can transform the optical assembly and create the waveguide optics, very similar to HoloLens, but with the advantage of higher performance, we believe, in terms delivered in efficiency, wide field of view, and overall brightness. The second aspect is that in waveguide optics, it's actually very difficult for optical engineers to design, because in fact many of the structures and methodologies for doing systems design isn't supported in CAD tools like ZMax and others. So what we've done over the years is develop tools which bolt on to standardized systems like that, which allow now optical designers for the first time to freely design these waveguide optics devices. And of course, after they've done the design and proven out the suitability and the performance, then move on to prototype these devices. So our mission is to get these tools out to the optical engineers so that they can design these waveguide optic platforms and so that they can deliver eyeglass-style waveguide displays. Thirdly, we had to develop new types of holographic printing machines, because clearly if you create these high-resolution nanoscale structures in the waveguide, which I'll explain in a moment, you then have to duplicate them in mass production, so it's extremely affordable. Currently, state-of-the-art is to do surface etching or surface relief gratings, and we use volume Bragg gratings using a photolithographic process. So there's a very fundamental difference and an opportunity to literally have our DigiLense waveguides cost cents rather than very expensive devices today. So with that platform, just a word about our business model, which is that we license manufacturers. So our mission is to get our machine tools and tools to the optical engineers and the manufacturers that are then going to produce the volume to serve the AR industry in a multitude of different product applications. So this is a little unusual, and we can do this because we have a full stack of technology to offer, and it's very affordable for a large-scale manufacturer to acquire this technology base and just get going in developing AR displays. And so far, we've been successful in having proven that whole transfer with our first customer in the area of aerospace. This is our first product, as I mentioned. It's actually the world's first, we believe, waveguide-based commercial civilian head-up display. And as of late last year, it was FAA certified. And we previously manufactured these parts for our client. We have multiple design wins in terms of the different aircraft manufacturers adopting it. But critically, we've transferred that manufacturing to one of our customers, Rockwell Collins, successfully. So they're now manufacturing this product for themselves and then allowing us to move on to other products, et cetera. And the point there is that we can effectively transfer. We have been successful in doing that. There is no reason why this technology won't deploy to multiple other manufacturers in that regard. This is a device that we're currently working on, which is translating the success in the world's first waveguide optic used for aerospace, but now into automobiles. And quite literally, the use of waveguide optics in automotive HUD design is revolutionary. It compresses all of the optical features necessary in a complex projection system that ordinarily would be composed of different refractive lenses and projection systems and very complex curved mirrors so that you can correct for the windscreen in front of the driver. All of that goes away. Everything gets written into the hologram, and all you need basically is to project an image into it. All of that complex optical system is translated in the waveguide and then output with a very wide field of view augmented reality display. So currently we're at 20 degrees field of view, but that actually comes down to approximately 15 when you introduce different types of curvature. In the most acute case, 15. In more flat windscreens, it goes up some from there. That's very important for the automotive industry because clearly they have demonstrated wide field of view, but typically the projection systems no less than 40 liters large. These are massive, great, bulky projection systems to create that kind of field of view. And this is down to fundamental physics. You can't get past it. Waveguide optics is a completely revolutionary new way of translating that then into a very thin form factor that can actually go into the actual car itself. So we're very excited about that opportunity of bringing augmented reality to automotive applications. And so it is today. I wanted to speak a little bit about our evolution from the wide field of view night vision type displays that we've been developing for military applications through to now consumer devices. We really see AR as a very long road, full of a rich set, a tapestry of different devices, adding the situational awareness and various other attributes needed for full augmented reality. And in that regard, we count ourselves really at the front end of that, where we're fundamentally as a company concerned with basic heads-up displays for safety and for visualization applications. We are moving towards augmented reality in due course, and those programs are now fully funded and underway, leading us to wide field of view waveguide optics for augmented reality. Just a little bit about waveguide optics, and I know this may not be in the developer community everybody's cup of tea, but I wanted to just drill down and explain in simple terms how these types of displays are created. Basically, I had mentioned earlier the proprietary materials, the nanoscale nature of these precision optics that need to be duplicated very cost effectively and with high yield. And that's very important if you're going to enter the consumer market and you want to see proper consumer prices, which I mean sub $500, sub $400 price points. And with that in mind, what we're doing using this contact copy holographic replication that I alluded to earlier is the ability to actually duplicate these structures, as I mentioned, very cost effectively. In our process, what we do is we take our material, we coat a sheet of glass, we encapsulate it with another sheet of glass, we expose it using something that's akin to a photocopier, except it has masters in it that are very high precision, and the pattern is duplicated from the master into the actual glass part, which I mentioned, which actually constitutes a waveguide. It's as simple as that. And an operator can then press and repeat, and obviously you can automate that process fairly efficiently, and that's exactly what we're doing as we move to higher volume in that regard. What actually happens when that scanning, or that photocopy process occurs, is that there's an interferometric pattern set up in the top left-hand corner there inside the actual waveguide. And the two interfering beams are creating an interference pattern which appears as like a grating structure with periods of high-intensity light and low-intensity light. And then our material system phase separates so that it forms these complex grating structures at nanoscale where you have regions of very high index, typically impregnated with liquid crystal, although we use other dopants, and very low index or index matching to the glass, which is a polymer, which is exactly matching. So you end up with a grating structure which we call high modulation, where you have periods of high index and low index, high index, low index. And of course, when the light hits that grating structure, it diffracts, and I'll come on to that in a moment. So these grating structures are composed of liquid crystal rich regions supplemented with other dopants. And as such, to give you an idea of how we were able to bring this kind of innovation through to waveguide optics and how we differentiate from other holographic companies or holographic manufacturers, by way of comparison, a typical off-the-shelf leading state-of-the-art material from major German vendors will have an index of modulation about 0.034. DigiLense is currently at 0.16, and we're headed very soon to 0.2. That kind of modulation allows for the gratings or the nanostructures to be very, very thin. And it's the thinness in Bragg physics that allows for the very wide field of view. So the wide field of view capability is directly and inextricably linked to the performance of the material systems that we use. And that's how we get both 100% diffraction efficiency and very wide field of view in our grating structures. The last two, lower left and lower right, really just shows, in addition, that we're able to electrically switch these grating structures. And it turns out with the electrical switching that there are many things you can do by having spatial temporal alternation between, say, eye tracking and then display, where visibly you can't tell that both systems are operating in a time sequential pattern. So there's many, many different optical architectures that can be created when you use the electrical switching within the actual waveguide itself. This just shows, this is actually a few weeks old, almost 100% diffraction efficiency. And this is the fundamental difference between Bragg, or volume Bragg grating, which is what the DigiLense platform is built on, versus the surface relief platform, which other companies use. Typical is Microsoft HoloLens, Vuzix, and other companies that are trying to bring product to market as well. We use volume Bragg gratings. And in a volume Bragg grating, you have this ability to have very high efficiency, and because of the thinness of the substrate, very wide field of view, and opens up the opportunity then to have eyeglass waveguide form factor for wide field of view devices. And I'll come on to that. This just amplifies the fundamental interaction of these diffractive surfaces. On the left-hand side, it shows the surface relief type gratings, typical for the companies I mentioned earlier and the examples in the street. And on the right-hand side, the DigiLense. Fundamentally, if you take an image and project it into a waveguide in a surface relief grating, you're going to get only a small proportion of that diffracting in the direction you want it. You will also additionally get multiple other orders, and suppressing those orders is part of the big challenge when you use surface relief gratings in terms of getting wide field of view. And in fact, you can't get wide field of view. It's down to physics. However, in volume Bragg gratings, you can, because all of the image goes into the first order and diffracts with very high efficiency, as the previous slide showed. So fundamentally in physics, volume Bragg gratings offers the opportunity to deliver the kind of performance that we need for advanced AR displays in the future. This was an example architecture of an exhibit that we did with BMW about a year ago at CES. Some of you may have seen this. It's where we used a display in a motorcycle to demonstrate the first waveguide display in a motorcycle application. That was very well received by the motorcycle community, who we care about. And in particular, we've then gone on to do a lot of intensive work in design to bring that type of waveguide-based AR display to HMD applications for consumer. And there are many, many regulatory standards that need to be dealt with, which I'll come on to in a moment, in bringing that to market. All this slide shows is that you take a projector, a little pico projector. It could be LCOS, could be DLP, it could be OLED. You inject it into the input, and in that input in the DigiLens, we're able to write structures in there that are highly efficient to that wide field of view display. In fact, we can change the director or the efficiency of the grading in a different three-dimensional axis to make sure that when that wide field of view image comes in, we actually take all of that image very efficiently into the super thin substrate, which is often only 1 millimeter thick. Once it passes into that substrate, it travels in the bottom right-hand corner, left to right, and this just shows an interpretation of a tracing in the actual optical system. And what it does then is do a horizontal exit pupil expansion. So it's now taking that pupil and it's replicating that pupil in the horizontal axis and stretching it, if you like, or replicating it many, many times. And then in that same structure, due to the three-dimensional nature of the structures we write, it sends it up vertically and stretches the pupil in the vertical direction, creating many, many pupils in the output. And thus, in the output, you have this very large eye box, typically around 25 by 25 millimeters, depending on many design constraints and how much light you have available. Because obviously, if you have a very large eye box, you might only be looking in a very small part of it with your pupil, which is typically 3 to 5 millimeters, and the rest of it's going to waste and just illuminating your head. So there are very strict requirements with regard to the system trade-offs that you have there, but ultimately you want a very large eye box so you don't have to adjust your eyeglasses, and you clearly can use it in a very active environment, say with sports or whatever. So that's one of the key attributes of the waveguide optics, is to generate a very large eye box, very high efficiency. And that is the fundament of two-axis pupil expansion that we're doing in the waveguide. These are just some of the tools that we've developed for optical engineers. For those of you more in the hardware track, these allow you to interactively design these type of waveguide structures and greatly improve efficiency of actually doing that systems design, which is needed so that you can go through the normal product cycle and develop products around this platform technology. There are many, many different creative ways that we've developed to actually manipulate light in these waveguides. I've demonstrated 3 or 4 methods just in that one previous example. And we call these optical IP cores. It sort of draws on the analogy of IP cores used in electronics design for chips, etc. Well, here, the system in the waveguide, so to speak, can have many different optical attributes, and that's how we classify them. And we think there's an opportunity for a designer getting hold of our CAD software and systems to actually take these cores and very rapidly then design the optical systems that they need to solve their problems in the device. In the particular example that I gave earlier about the two-axis pupil expansion, this just really amplifies the difference between the type of gratings that we can write using volume Bragg technology versus surface relief. And in volume Bragg technology, we can use one particular structure called this roll K-vector, which allows us to three-dimensionally change the diffraction efficiency of the structure across a spatial area. And this is very important because if you're going to put a wide field of view image into that waveguide, you need to have it be 100% efficient at the 2 corners where the angle's coming in at a very slant angle, versus in the center of the field of view where it's coming in perpendicular to the waveguide. So it's important to have very high efficiency across the range of angles, and we would argue that only volume Bragg technology allows you to do this and then skew and then necessarily get the requisite efficiency that you need in the waveguide structures. And typically, just as a version of measure, and this isn't normally known, but what we're looking at in something like a HoloLens, which is a surface relief technology used by several companies, so it's just an example, is an overall efficiency that is measured, at the % or lower, overall phototropic efficiency in the device. And this is because when you have the actual surface relief structures, which are relatively inefficient across the optical train, you get cumulative deficiencies, if you like, in the system. Using volume Bragg, where we have these structures that can be very high efficiency, we can considerably improve on that. And we're talking order of magnitude improvements in overall efficiency in that regard. So fundamentally, we have a way of giving longer battery life and wider field of view, whichever way you choose to actually take those kind of performance improvements. This is an example then of the what we call the Mono HUD, which is our first consumer product. And this builds on the experience that you may have seen at CES when we launched with the demo. I'll give an example with BMW. And what we've done then is to invest heavily since that time over the last year to create a new type of device which we're bringing to market this year. This just shows a little video segment showing how we envisage this type of display can be fitted into a helmet.
Head-up display I told you about.
The key point here is it can be fitted into any helmet. It's a very simple system. You just pull back the pads on the helmet, fit the unit in with some Velcro straps, and once it's fitted, it stays there forever. It can fit into any helmet. Very inexpensive. And the whole point is that you can detach the waveguide. We showed this at CES. You know, this waveguide optics is not at super high precision. You can have a lot of tolerance in the system. We use the Mag Connect, so you literally plug in the waveguide as and when you want to use a head-up display, in this case for motorcycle applications. Obviously mapping is the traditional and you know, well calibrated application. Interactive feedback from other motorcyclists. Really the whole mission here is to make motorcycling more enjoyable. It's kind of like snowboarding, it's all about A to B. Well, it shouldn't be. It should be about a journey together in the world, looking around you, interacting with the environment, and really transforming this whole idea of traveling together with the system. That's really where we're headed. Obviously for now, we're very focused on very safe, non-distractive graphics to augment the actual scene. And today it's important to recognize that there are products out there for motorcyclists which are literally based on the iPad or on the iPhone. And these guys literally Velcro it to the fuel tank. That's not a safe solution. So in that regard, we think that bringing this type of technology to motorcyclists and other HMDs I'll come on to will greatly enhance the experience, so entertaining, but critically it's a much safer solution than that's currently offered, you know, with existing examples in that regard. So with that all in mind and bringing heads-up displays and the safety aspect from aerospace and automotive now to the consumer for motorcycles, there are other applications also which can greatly enhance that. A word about optics here. We are collimated in the distance. Typically in heads-up displays, you like to be around 7 to 7.5 meters in front of you, which is typically where, you know, traffic as you're flying would appear, and obviously not allowing you then to have to refocus if something was closer or further away. So typically about 7.5 meters is the aim for the collimation. It's a basic point that whatever level of collimation or divergence or convergence that you put into the waveguide, you will translate out of the waveguide. So the waveguide is agnostic. So if you want auto accommodation, there are ways to auto accommodate just by using a variable lens in the actual projection system, and so it is that you can move the focal plane on the output, and I'll come on to that in a moment. So fundamentally you have a platform that's sort of like an eyeglass style optical periscope. You go in and then come out with the advantage of doing the two-axis pupil expansion to allow you a very comfortable and wearable display in that regard. I won't go too much into the specifications, but one of the most important things to recognize when you're bringing a product, especially on a safety track, to consumers like motorcyclists and others, is that of being compliant with regulations. There are 6 different international standards, regulatory standards, one of which is DOT, which is the US standard, which is the high bar, if you like. It took us nearly a year to design around and make sure that we are totally compliant with those regulatory standards in terms of distraction, and in particular, in terms of supporting a full field of view without any form of obscuration in the peripheral field of view in particular, because obviously if a truck comes up alongside you, you never want to have the motorcyclist be anything less than fully observant of that peripheral field of view. for obvious safety reasons. This is what we call our field trial version, and this is a version that we fielded in actually March of this year, and it's been on user trial since then and continues. And we're getting all the feedback and data with our public partner, which is BMW, testing on racetracks and various other places, and we have several other customers which aren't public that we're also working with. But it's invaluable to get that feedback and to ensure that not only do you meet technically the regulatory requirements, but that the display itself is actually field trialed and thoroughly tested in the domain, as we did with the Aero HUD that we manufactured. So in that regard, I would say that it's very, very difficult to make an obscuring look-at display, even a look-down display, and actually be compliant with those regulatory standards, even with the advantage that we have with a wraparound waveguide to within a couple of millimeters. It's a very tight design space. So we spent a lot of time working on those regulatory standards to ensure that when we bring this product to market, it's a safe and very usable product. This particular device, well, if you stand back from it, it's really the union of two, pretty well developed, well, one pretty well developed, but two fundamental technologies, a Pico engine by DLP and ourselves with the waveguide. And it's the union of those two where they're actually in quite a high state of readiness, so to speak, on the Pico side. It's very good étendue, very good efficiency on the LED collection, the DLP chip, very low cost, very small form factor, all the ideal requisites that you need in those components to actually build something that's all-day wearable, and critically bright enough. In an outdoor all-day wearable display, like a motorcycle display, you must have the requisite brightness to satisfy, literally a very sunny day right through to, obviously nighttime use. So in that regard, we've recorded now with this field trial unit 14,000 nits. So 14,000 nits is almost uncomfortably bright. And that's really the union of the Pico projection fidelity and the waveguide efficiency that I alluded to earlier coming together to give you that daylight brightness. And that daylight brightness can be cut and sliced in many different ways. You could take it as very high efficiency and hence have longer battery life, or you could take it as all-out brightness when you're staring into the sun on a sunny day. And you literally can stare just below the sunline and still see that kind of brightness display. Many different applications in motorcycling, as I mentioned, and meeting all the regulatory standards. It's important to recognize you just unclip this waveguide. The actual projection unit stays in situ all the time. You just use it when you want to use it. And that kind of utility is again, very important to get broad-based consumer adoption of AR-type displays like this. I tested it personally. in the goggle all day, and again that was very usable, and when the display is not being used you don't have any visible impediment to your field of view. We're 94% transmission efficiency with these types of waveguides, so it does afford you very clear field of view in the real world in that regard. Obviously for cyclists there are many different applications that this can be applied. And of course, gaming. It's very difficult to actually film AR displays through the waveguide because the camera has difficulty focusing on the other side. But you can see this little early version that we took showing what a gameplay might one day look like in that regard. And it's a very low resolution video just shot with an iPhone, but clearly, as I mentioned earlier, as you see the display and can superimpose various characters, if you have the 6-axis rotate sensor plus any proximal detection, you can then take it to the next step of AR displays in that regard. And you can see that the waveguide optic, this is a 40-degree field of view, one can be simply unclipped and used as and when you need to in that regard. This is our prototype, which goes beyond the field trial and produces something very much slicker and a very wide, a slightly larger eyepiece. It's critically important in AR displays that people on the outside can see very clearly the eyes of the people using that display. And in that regard, we have something that can be very usable and not off-putting by other people. We intend to bring this to market in a multiplicity of different points and at a consumer price point later this year.
Awesome. Round of applause.
Thank you.
Please.